Hi, everyone. So for the next 40 minutes, I'll talk about barrier methods and a bit about first-order methods. Timo mentioned that I work mostly in conic optimization, and that's kind of just a special case of the barrier methods I'll talk about today. So if I have time, maybe I will sketch a few extensions. So the linear programming problems we'll talk about are the same as Julian used. A primal problem where we minimize C transpose X. We have equality constraints, AX equals B, and X is non-negative. And we have a dual. We maximize B transpose Y, and C minus A transpose Y is also non-negative, or it equals S, and S is non-negative. So the optimality conditions, I like to put them in a compact form like this. It's just a restatement. The top row says that AX equals B and C minus A transpose Y is S, X non-negative, S non-negative, and then strict complementarity. And the reason why I like to put it in this form is that we're going to use it repeatedly when we get to algorithms in a few slides and for the rest of the talk. But something that's already nice from this formulation is that suppose we have a solution to this system. So we solve this linear system, X and S are non-negative, and we have strict complementarity between X and S. Then we see immediately by multiplying with this vector from the left, then this term disappears because this matrix is skew symmetric. So we immediately see that C transpose X minus B transpose Y is X transpose S, and since we have strict complementarity, this kind of follows immediately from this way to write the problem. So what is the talk is about barrier problems, barrier methods. What is a barrier method or barrier problem? There are different ways to define it, but one way is just to say we have a primal barrier problem where we augment the objective by a term including the sum of logarithms of the xi's. So this would be the primal barrier problem, and it's for a specific centrality or a centrality parameter mu that is greater than 0. So if we say what is the Lagrange function for this, we write it out. It's just the objective and then Y transpose the constraints. Then we immediately see optimality conditions. AX equals B, X is 0, and then the derivative with respect to X of this function is the interesting part. We see that C minus A transpose Y is a scaled version of X inverse, and that's what we normally would call S, right? So this term here would be S, but now it's not S, now it's a scaled version of X inverse. We could also write a dual barrier problem, then we augment the dual problem by a sum of logarithms, and we could derive optimality conditions. And turns out they're the same optimality conditions, exactly the same. So the primal and the dual problems, they have the same optimality conditions for the same value of mu. And that leads to one definition of what we call the central path. The central path is essential in these methods. So it just means that if you solve this problem and this problem for a particular value of mu, and then you take the X, the S, and the Y, then these 3 points, they form a continuous curve through the solution space from some interior starting point, and then you form a continuous curve all the way to some optimal solution at the boundary of your feasible set. So that's the central path, and the whole point about what I'll talk about, barrier methods or interior point methods, the point is that compared to simplex, where you try to go vertex by vertex, then you try to follow this continuous smooth curve through the interior of your solution space towards some point on the boundary. So that's kind of loosely what the central path or path following method is. So moving on, let's restate the optimality conditions from the previous slide in this. So that's exactly the same as before. Only thing is that now we relax strict complementarity by this, that x times s is some small number mu element-wise. So it's kind of a relaxation of the original optimality conditions. And as we decrease mu towards 0, we expect to convert to an optimal solution. So this is a different way to just write this central path. And the rest of the talk is just going to be, how do we linearize this central path and solve it with Newton's method? And that's essentially what a primal-dual interior point solver does. So let's get on with it and linearize these central path equations. So the first equation, ax equals b, we just linearize like this. The second one, c minus a transpose y equals s, is just linearized like this, straightforward. The complication is the centrality condition, and that's kind of the only non-trivial thing about interior point method. That is, how do you linearize the centrality condition? For linear programming, it's still fairly simple. We have x plus delta x times s plus delta x equals this number mu. So in the linearization, we just throw away the higher order term, delta x, delta s, and then we're left with this. So x plus delta, x times delta s plus s times delta x is equals this right-hand side. So that's, that's almost it. We just have to solve these repeatedly. And to get towards a practical algorithm, the first thing you'd normally do is to eliminate delta s from the centrality condition. So if we just eliminate delta s equals the right-hand side times x inverse minus x inverse times this, plug it back into plug it back into the second linearized equation. Then we get a system like this. It's just a system block set of equations with two variables, delta y, delta x, and it's a non-singular coefficient matrix under the usual assumptions that in an LP like, so no one actually mentioned this in the previous slides or the previous talks, but we kind of assume in this formulation that A is a matrix with more columns than rows. So in other words, we assume all the rows are linearly independent. That's kind of an assumption we work with. But under this assumption, this is a non-singular matrix. We could just solve it. We solve it for this right-hand side, and then we get delta x, delta y, and then we find delta s from the centrality conditions. We have to solve for delta x, delta y, delta s, the three unknowns. We can just solve this system and compute a suitable step size. That's a linearization of the central path and essentially what a primal-dual method is. So let me just sketch kind of the steps of a practical algorithm. And I would say for linear programming, people totally know how to implement it. And you can look at this. I have references at the end of the talk. There's a very famous book where you will find this material also. It's a kind of a dated book, but that's what people do. And when I mean people, I mean professionals, companies, and it works really well. So we start by just picking an interior starting point. X and S could be all ones and Y could be 0. We evaluate primal and dual residuals. And if the residuals and our complementarity is 0, then we terminate. If it's not 0, then we first compute what is called the affine search direction. And the affine search direction is the same as what we have here, except we cancel this centering perturbation. So we solve this linearized central path equation, but we ignore this term. And if we can take a full affine step, meaning we compute the search direction, and if then x plus delta x and s plus delta x is in the cone, we can take a full affine step, then we're done, then we can just finish, because then we have solved the original optimality conditions without the perturbations. Normally, that's not what we're shooting for. We're just computing this affine search direction to use for another heuristic that we'll get to. But anyway, the third step is computing the affine step direction, and then affine step size for the primal and dual variables. Have to pick a step size between 0 and 1 that remains within so that the updated x and s remain non-negative. So the next step in this practical method, which is in some way completely ad hoc and just works remarkably well, is to choose kind of an adaptive centering parameter. And most often it's defined something like this. So it's something that's defined experimentally, or not defined, but I mean, it's an experimental rule, so different solvers might modify it. But anyway, it's something like the ratio between the updated complementarity, so the updated x transpose times the updated s over the normalized by the original centrality. So the improvement in centrality to the power 3. So that's kind of an adaptive centering parameter that people have found out it works really well. And once we're equipped with this centering adjustment and our affine search direction, then we compute what people, we compute our final search direction, where we just modify the centrality condition. So you see this centering term is scaled by this adaptive parameter, which is between 0 and 1. And then we have this term here that involves the product between this affine step for x and s. And if you recall, when I talked about linearization here, I said, well, in linearization, you throw away the higher order contribution. This term just is meant to compensate for this higher, it's a higher order correction that compensates for this term you threw away in the linearization. But those are kind of not that they're ad hoc improvements, but they help a lot. And normally people would call it kind of a Mirod predictor corrector method. So if you come across that word, this is just, this is what it is. It's linearizing the central path and then adding these ad hoc improvements. And then you take a step you update your steps, you scale them down a little bit so you don't step exactly onto the boundary, you have to remain interior. But that is kind of the LP solver that you will find to some extent in many commercial solvers, and it works really well. So that's one algorithm. I would say people that really know how to do it, that this is the way to write a primal-dual LP solver. So this system, that's something we had to solve. In the way I like to write it, I mean, maybe it looks unsymmetric. It's not really unsymmetric. If we change sign of delta y, we would change the sign here also. Then it would become symmetric. So we could solve this, and that is what people call the augmented system approach. And your colleague, Mesa Sabros, he is famous in the whole industry for knowing everything about the augmented system. Isn't that true? I think. Yeah. Yeah. I think most other vendors, they solve what people call the normal equation using a Cholesky approach instead. So what we do from here is we eliminate delta x from the bottom equation, and then we plug that into the top equation. Then we get a system like this. We have A times a positive diagonal matrix. And I'm sorry, I never said what capital X and capital S is. I mean, it's so often used in linear programming literature that I forgot to mention it. Capital X is just our vector S put into a diagonal. So it's a diagonal matrix with x's on the diagonal. I should have mentioned that in the beginning. So this is a diagonal matrix, and in all other places where I used capital X, I used a capital X and a small s, then that is actually just element-wise products of X and S. So my apologies. But anyway, so what I was saying is that then this is A times a diagonal matrix times A transpose. That's a positive definite matrix. You can just factor it using sparse Cholesky for delta Y. Once you have delta Y, you back substitute and solve for delta X. And then we solve for delta S from the centrality conditions here, right? That gives you delta S from this equation. So we solve for delta Y first, and delta X, and then delta S in the end. So we use sparse Cholesky. Since we use sparse Cholesky, it's important to reorder rows and columns of this matrix to reduce fill-in, and it's important to handle dense columns in A separately. If A had a dense column, then that would generate. If there was a dense column in A here, then this product would be very dense. So the density propagates. So that's two things that I'm just saying it's important in a real implementation to use row and column permutation and then handle dense columns separately. And this algorithm assumes that that there is a primal and dual feasible point to both. In other words, that you have the primal problem and the dual problem attain the same value. If it's infeasible, then the algorithm just doesn't converge. So that's a kind of, but still it's a useful algorithm. So what I'll move on to is what happens if your problem is not feasible, either the primal or the dual. How do you detect it? And how do you cope with it gracefully? So the method that is almost always used is the homogeneous self-dual embedding. And there are two variations of the homogeneous self-dual embedding. I'm talking about the simplified one, where you just add two variables. You add a variable tau and kappa. They are non-negative variables you add to your problem. And then you embed your optimality conditions into a larger system like this, where you see that the first row just says that A times X equals B, but scaled by tau, and similar for the others. And then you kind of have a gap equation at the bottom that B transpose X minus B transpose Y minus C transpose X is kappa. So this system is very much related to the lecture by some of the elements in Ambros' lecture about theorems of alternatives and Farkas certificates. So I'll just go over it quickly, but I'll say this system always has a solution, right? You could just check that the zero solution solves it. The algorithm would try to steer you away from the zero solution and get a solution with strict complementarity so that X and S are strictly complementary, and so is tau and kappa. So assume we have found a solution, a solution which is with strict complementarity, meaning that not both tau and kappa are zero at the same time. Then if tau is greater than zero, then kappa must be zero. And then we just normalize X, S, and Y by tau, and then we have the usual optimal. Then we have a solution that satisfies the usual optimality conditions. If otherwise, if kappa is greater than 0, then tau must be 0. And then either we have a certificate of primal infeasibility or a certificate of dual infeasibility, or both. So that's kind of the simplified homogeneous embedding. So what we need to do is just to redefine the central path and then do everything once more just for these set of equations. And we just have, instead of x and s, we just have two variables in addition. And now the primal and dual step sizes, they're kind of linked by the gap equation. So we just have one step size. So linearize the central path, make a simple step that remains within the non-negative orthant. And yeah, that's what it is. The practical algorithm, choose a starting point. We need to set tau and kappa also. Evaluate our residuals. Our residuals are different now because scaled by tau. And also the gap equation, that's something we didn't have that before. If all these residuals are small, then we terminate. Otherwise, we compute the affine search direction and a step size. We compute a centering parameter. So this looks different from before. It's the same expression as before. It's just simply the ratio of reduction in complementarity just simplifies when the primal and dual step size are the same. So this expression is the same as before if we also added the tau and kappa contribution. But anyway, we define our adaptive centering parameter. And then we solve this system, everything as before. And then we take a step towards the boundary and scale down. So we are 20 minutes in and we have two practical algorithms already you could go home and implement, and they would work relatively well, I'd say. I mean, it's not that much more that are in the commercial codes, at least not, I mean, from this level. One thing that's a little different is when we, to solve the linearized central path equations, we kind of know what to do when we just have a 2x2 block system. We talked about that in the infeasible method. Now we have a bordered system, so we just need to discuss what to do with the border. So the first thing we'll do is to eliminate delta S and delta kappa from the centrality conditions, and then end up with just one set of equations like this. So now it's a 3x3 block system we solve, and this is a non-singular system, so we can solve it. We solve it for delta y, delta x, delta tau, and then we find delta S and delta kappa from centrality. To solve this 3x3 system, I'm just going to state what is normally done and then say it's actually easy to verify that this is true, and that this is the case. It is easier. It's kind of easier to verify than to derive. So just stating this is what you do, then the verification is easy. So just like we solved systems for the infeasible method with this 2x2 block system, we solve similar systems, but for two right-hand sides, for the leading part of the right-hand side and then for the leading part of the border. From these two solutions, it's easy to find delta tau in this way, and then you find, once you have delta tau, you find delta x and delta y by a combination of the two. So I'm going to stick with my claim that this is easy to verify. I think it is easy to verify, and that's how it's normally solved. So this 3x3 bordered system corresponds to just solving the 2x2 system for two right-hand sides and then combining the solution. In the infeasible method, we had to solve two systems. We had to solve the affine search direction and the combined search direction. So two solves of the 2x2 block system. Here we have to solve still affine and combined, so it accumulates to 4 solves, you would think. But this is the border, doesn't change from the affine search direction to the other. So it's true that we're solving somehow 4 linear systems, but one of the solves can be reused. This when we're solving for the border. So we end up, instead of solving 2 linear systems from the infeasible method, we end up solving 3 linear systems. So that's a very moderate cost for handling infeasibility gracefully. So I think I'm okay on time to maybe talk about what do you do when we move beyond LP. So I'd say from a commercial point of view, the second most important thing after, well, maybe after LP, QP is important, and then you have second order cone programming. So second order cone programming is maybe some of an area where I spend a lot of time. And so I mentioned in some of the early slides that kind of the complicated thing is always how do you linearize the centrality condition, and that's the so that's really the case for second order cone programming and also semi-definite optimization. You can represent your complementarity conditions differently by scaling X and S by some matrices that comes from the Hessian of your barrier at a special point. And that is called a Nesterov-Tott scaling. Doesn't matter what the matrix is. The thing is just you have an equivalent recharacterization of the central path where this is a product. For linear programming, it's just element-wise product. For second order cone or SDP, it's something else, but it's still a simple bilinear product. So once you have this equivalent recharacterization of the central path, then you linearize it like this. So this looks very much like before. Here we had S and here we had X for linear programming. Now we have this scaling matrix that comes from this sort of Tott scaling. And if we go back, everything that changes is just that in the 2-2 block here, then we're going to get this W squared. So this Nesterov-Tott, the squared Nesterov-Tott scaling is going to appear in this block. Otherwise, it's business as usual, mostly. And that was pioneered by Sedumi and SDPT3. And so those are kind of old papers, but they form the basis of kind of everything we do in the conic framework and what commercial cone solvers like ours, FICO, MOSEC, they all owe a huge debt to Sedumi and SDPT3. And if you're into this stuff, you should read the papers. They're still relevant, even they are 25, 30 years old. So this is a slide that kind of tries to highlight the difference and benefits between of simplex versus barrier. Maybe I'll go over it a little bit quickly and just say that maybe barrier is, maybe simplex is better suited for extremely sparse, and if you want to do MIP re-optimization, it relies on LU factorization, whereas the barrier method relies on Cholesky factorization, or if you solve the augmented system, you have to do something else. So the last the last 5 minutes, I'm going to talk about first order methods, and I don't want to give you the impression that it's kind of a lecture on first order method, because that could it's not. It's just I'm taking out one method that has gained some popularity recently, and it's called the primal-dual hybrid gradient method. And it's kind of a splitting method that minimizes f of x subject to linear constraints, where f of x is just a closed convex set. And often in the literature, you actually, or when you call it a splitting method, it's because you don't minimize just f of x. You kind of have the constraint put into a different function, so you minimize something unconstrained, f of x plus d of x, and then you have the splitting. But this is kind of simpler and what we really need. So I'm sticking with this simpler notation. So the Lagrange function for this is just, of course, the objective, and then y transpose your constraints. And that gives you a dual that is just, the dual is just minus the conjugate function, the conjugate of A transpose Y plus B transpose Y, where this is the definition of your conjugate function. And that's, I mean, maybe that it looks a little unusual if you're just used to primal-dual LP methods, but it's kind of a standard thing in first-order methods. So the solution is a saddle point of this, and the solution is a saddle point of to this, and the optimality conditions we have is that A transpose Y is a subgradient of F, and so all of this is kind of comes from subgradient methods, and that's a lot of theory and subgradient method that goes back to the, well, even before the 70s, but it has kind of regained a lot of popularity. And but anyway, those are the optimality conditions. AX equals B and A transpose Y is a subgradient of F with the usual definition of the subdifferential. And so then what is in this method that was developed by Puck and Combet, then they proved that, well, for a problem like this, if you have update equations like this, then for fixed primal and dual step sizes, then this iteration converges to the optimal solution, provided that your steps are not too large. And by not too large, I mean that the product of the primal and dual step sizes, like times the squared largest singular value of A, has to be less than 1. So if you choose your step sizes fixed in a way so that this is satisfied, then this iteration scheme converges. And so that what is in this iteration scheme, Y is just a simple affine update. You take the difference between x's and then you multiply by A and then scale it. The update for X involved what is called the proximal mapping, or in the original paper by Combet and Puck, they talked about resolvent operators, but that's the same. So you just have to do a proximal mapping. So compared to the method we saw before that required factorizations, all we need is to multiply by A transpose, and then we need to evaluate the proximal operator. So it could be that that proximal operator is not easy to evaluate. For instance, for SDP, if you just straightforward want to apply this for SDP, then you would have to do an eigenvalue decomposition over and over again of a large matrix. So this wouldn't be a great idea. But Combet and Puck, they used it for total variation in imaging, which is kind of related to, you could also formulate that as a second order cone problem, but they used this subgradient approach. I don't think they had imagined it would kind of be used for LP, but that's what happened, and it didn't really get onto my radar before people started using it for LP, especially Google popularized it. So what is PDHG for LP? Well, it's just replacing our f of x by the usual linear objective times an indicator function for the convex set you have. And if you do that, then your proximal mapping is just going to be, so this is the definition of your prox function. You minimize C transpose X, tau times C transpose X plus the Euclidean norm of this difference. That is just a projection onto C, shifted projection. So a prox operator is just projection onto the non-negative orthant, so truncating negative elements. Nothing can be easier than this, right? So this is PDLP, popularized by Google. This simple affine expression project onto the non-negative orthant, and then similar for y. And if we had used this this other formulation with a additional function called g also over a closed convex set, then we would have projection here also. But otherwise, it just looks like this. So we had this optimality condition, which was at least to me confusing when I first saw it, that A transpose Y is a subgradient of F. What it means in this case for F is just that the subdifferential of F is just C plus the normal cone. So the subdifferential of an indicator function is its normal cone. This is the definition of the normal cone. So then another thing it's not easy, but it's not hard either, is to show that, well, this boils down to the usual optimality condition, C minus A transpose Y is S, where S is the minus D you have here. So good news is that we kind of have things we're used to just from LP. But that is PDLP, and my employer Cardinal has invested a lot in that algorithm and improved implementations, including heuristics for better step size selection and also other heuristics. And I would say it's probably not a replacement, a general purpose replacement for an LP solver, but for some special super large sparse problems, it's maybe a better alternative. And we have some, those are just different instances from the MIP-LIB tested where the root LP can be non-trivial to solve. And we see that kind of for the first class of problems, barrier is definitely better than simplex, and probably PDLP on a GPU is better, at least for the largest. Same goes here for the satellite instances. Barrier is better than simplex, and maybe PDLP is faster. And for the unit commitment problems, probably simplex and barrier are better. But those are kind of selected problems, but it still shows you that at least with these first order methods, we can already have a realistic alternative to established methods that people have been using for 30, 40, 50 years. Some of the active research areas are theory and algorithms for non-symmetric cones. That's, we don't have second order cones or SDP, you have other cones, but non-symmetric. What do we do? GPU implementation, exploiting sparse structure and SDP is kind of the everlasting research topic. And first order method, I would say just anything is at play because people in some way know so little about first order methods. So it's the theory, the algorithms, heuristics, other methods, and GPU implementation. You can kind of do everything. COpt is easy to install. It's easy to use, and it's easy to install from Python, Julia. Just use pip install or use Julia's package manager. You don't need a trial license. Can just get the default. Some of the important references, let's give credit where credit is due, is of course Stephen Wright's book, which is kind of dated, but still a great book. And everything I said about infeasible method is from that book. Jo Styrm's papers are a must read if you are into that kind of stuff. Then there's Chambol and Pock's amazing paper that came out in a mathematical imaging journal. Maybe that's why it kind of flew under my radar. And Applegate and co-authors, they kind of popularized it with the Google papers for LP. And then I'd say my good friend Lieven Vandenberge, he has amazing lecture notes about these first order methods. So if you're into the first order methods, you should check out his lecture notes for sure.